Before we look at Green's theorem, we're going to look at a little bit of vocabulary. Suppose we have a region D that is bounded by a curve C. Assuming T is a parameter, C has a positive orientation if the bounded region is to the left of a point on C as T increases. In other words, if you were a little ant walking along the curve C, then you'd be walking in the positively oriented direction if the region that it bounds is always on your left. C is a simple curve if it never intersects itself. So I'll underline positive orientation in simple curve because that's what I'm describing here. Now for Green's theorem. Let C be a positively oriented, simple, closed curve in the plane, and let D be the region bounded by C. Of course, that's not the statement of Green's theorem. But one thing I'd like to point out is that the closed curve is in the plane, which means we are in 2 dimensions. Sometimes you see subtle things like that require a little bit of mental interpretation when you're reading math. If functions p and q have continuous partial derivatives on an open region containing D, then the line integral over C of p dx plus q dy, we've seen that before. What we haven't seen is that that line integral is equal to the double integral over D of the partial of q with respect to x minus the partial of p with respect to y dA. Folks, this says that a single line integral has the same value as a double integral. Now, as a reminder, if we have a vector field f that is given by pi plus qj, then this whole thing is the line integral over c of f dot dr. So what Green's theorem does is it gives us a new way to compute f dot dr as long as the stated requirements for C hold. Note that also among the statements, right, is that C is closed. We're going to see a partial proof of Green's theorem. And this partial proof is actually only in a special case. It's in the case that D is both a type 1 region and a type 2 region. I'll remind us what that means in a minute. Our author calls that a simple region. A type 1 region is one in which D can be expressed as a set of ordered pairs xy such that x is bounded by constants a and b, and y is bounded by functions of x, say g1 of x and g2 of x. A type 2 region is one where D is a set of points xy such that x is now bounded by functions of y, say h1 of y and h2 of y, and y is bounded by constants, say c and d. I think a picture would be in order. So here we have 2 representations of a region D. On the left, we're envisioning it as a type 1 region, and on the right, we're envisioning it as a type 2 region. And the idea is for a type 1 region, we have an upper boundary curve, which is G2, and a lower boundary curve, which is G1 of x, right? So these curves are functions of x. And then for the type 2 region, we have a leftmost boundary curve, which is h1, a function of y, and then a rightmost boundary curve, which is h2, a function of y. So this is the type 1, type 2 business. Now the boundary curve is C, and we're going to break it up into a C1 and a C2 for the type 1 region on the left. Notice we now have an orientation for the curve C. That's required all around because in the statement of Green's theorem, we need a positively oriented closed curve. And now we'll remind ourselves of what Green's theorem says. The conclusion of Green's theorem is that the line integral over C of p dx plus q dy is equal to the double integral over D of the partial of q with respect to x minus the partial of p with respect to y dA. Since that's its conclusion, showing that we have 2 things that are equal will suffice to show that the equation is true. And so we're going to show that equation, well, I'm calling it equation 1, says that the line integral over c of p dx is equal to the negative of the double integral over d of the partial of p with respect to y dA. That's what I've underlined in blue up there. Showing that that and equation 2, which is the line integral over c of q dy, is equal to the double integral over d of the partial of q with respect to x dA. That's the one I've got in green, showing that these two are both equal to each other, or rather these two equations are true, will let us say, well then by adding these two results we end up with the statement of Green's theorem. In other words, showing that these two equations are true would suffice to prove Green's theorem. Focus on equation 1, and in fact we're going to focus on the right hand side of equation 1 for now. We have the double integral over d of the partial of p with respect to y dA. That's the expression given in the right hand side of equation 1. Based on our view of d as a type 1 region, we have that we can express this as a double integral with c2 as the upper boundary and c1 as the lower boundary. Those are what we call g1 and g2 of x. So the partial of double integral over d of the partial of p with respect to y dA then becomes the integral from a to b of the integral from g1 of x to g2 of x of the partial of p with respect to y dy dx. Well, since this is the partial of p with respect to y, integrating with respect to y is going to give us the integral from a to b of p. Now, p actually takes in more than one variable, right? It's x and y, otherwise this wouldn't need to be a partial. So p of x g2 of x minus p of x g1 of x. The whole thing will still be integrated with respect to x, but that's going to be a stopping point for us for now. And the reason that g2 and g1 are showing up as the second coordinate of the input for p is that that would be y, and we just evaluated for y. Now back to equation 1, we're now going to look at the left-hand side, which involves the curve c, and it's the integral over c of p dx. Well, that line integral over c of p dx is a combination of a line integral over c1 and a line integral over c2. And in fact is the sum of those two line integrals. Using what we know about the orientation of line integrals, we can say that this result equals the line integral over c1 of p dx minus the line integral over negative c2 of p dx, which then becomes the integral from a to b of p of x g1 of x dx minus the integral from a to b of x g2 of x dx. Now, what was the reason for changing the orientation here of c2? Well, by doing that, c2 will then go from the point A to the point B. I should say negative c2 will go from the point A to the point B. So its input variable would go from A to B. c2 itself, the way it is, would have limits that go from B to A. So there's the kind of reversing the limits gives us the negative of the integral. And because those limits now match, we can combine these into a single integral. That integral being the integral from a to b of p of x g1 of x minus p, oh I left out a p there, of x g2 of x dx. Now, look what we've done. Here we've got xg1 of x as the argument first and xg2 of x as the argument second. But in our previous work, when we looked at the right-hand side, we had xg2 of x as the first argument and xg1 of x as the second argument. These started out with the right-hand side of the equation that we started with and the left-hand side. Therefore, it follows that the integral over c of p dx must be the negative of the integral over d of the partial of p with respect to y dA. A similar type 2 region argument would finish the proof for this case.